Hello everyone, welcome back to Comp 3430 Operating Systems. I hope that you all had an excellent weekend. I went yesterday to a place called Activate. Have you all been to Activate before or heard of it? You've heard of it? Yeah, you've heard of it, okay. This is not a class that's sponsored by Activate, to be clear, but I really love that they are a Winnipeg company, and like they hire co-op students, and they are a multinational company at this point. Like they are selling the rooms that they have. So if you've never heard of Activate before, it's a place where they have these different activities in a bunch of different rooms that are kind of like set up as giant games that you play in. So it's not really video games where you're playing with a controller. You're like, the room is the controller and you're doing all sorts of stuff. And one good example of this is they have a room where it's called Grid and Mega Grid, and the floor is just, it's tiles that are colored LEDs, and there's a lot of different games where you have to like run and stand on the correct color of LEDs before some timer goes off. And it's a great deal of fun. It's a lot of fun. I had a lot of fun. My kid had a lot of fun. The one problem that I have is that I'm becoming an old person now, and when there are games like there's a bunch of green lasers that are shooting across the room and you have to like duck and jump to avoid them, I can really feel that the next day. I can really feel that the next day. Yeah, I will note that I rode my bike here today. I am super happy to have done that. There's not much ice. It was kind of cold this morning, but there's not much ice and there's lots of sand, but it's good enough for me and I'm happy to take it and I'm happy to be biking. So welcome back to Comp 3430 Operating Systems. By the end of today's lecture, what I want you to be able to do is, first and foremost, I want you to know a little bit more about Assignment 3. This is the last assignment that we're going to have for the course, so I'd like to spend some time talking about what's expected overall, what we're doing for the assignment, some of the things that you should try to do when you're working on the assignment, and how you're going to be assessed on the assignment. And then after that, what I want to do is I want to spend some time taking a look at some more scheduling policies. So last week, the scheduling policies that we looked at were all non-preemptive. They were all cooperative multitasking, except in the examples that we were doing, nobody was actually cooperating. We just ran these jobs until they were done to try and decide which task gets to go next with the scheduling policy that we were looking at. We didn't really evaluate the performance of scheduling policies in the form of like calculating the average response time and the average turnaround time, but that's something that you can and should do on your own to try and make sure that you can make comparisons between different scheduling policies. Our main focus was on this idea of fairness, and this led us down the road of thinking about what happens when we have an infinite number of tasks in a lot of cases. But we can begin to say that even if we have an infinite number of tasks for some scheduling policies, it's fair because we will eventually get control of the processor given an infinite amount of time. Where with other scheduling policies, even with an infinite amount of time, we can show that given an infinite number of tasks, we will never get control of the processor under certain circumstances. So that specific case was shortest job first, where we have a longer running task and there's an infinite number of shorter tasks that always get to go before it. So at McDonald's, holding the door for everybody going in to get their food and then never actually being able to go into the restaurant to place the order because you're stuck holding the door for everybody going in to get their food. What I'd like to look at today with scheduling policies are some preemptive scheduling policies. So what happens when we actually start to be able to regain control of the processor after a task has started running on it? And then I want to start thinking about how that affects this idea of fairness. So if we are able to regain control of the processor, can we show that this policy is fair based on properties that we have of the tasks that we're working with? So first and foremost, let's take a look at Assignment 3. So I posted this up on the course webpage just this morning, so if you haven't logged into UMLearn, you may not have seen this yet. There's a couple things that I'm going to take a look at here, both a Git repository and the assignment description itself. This assignment is going to have us working on implementing some concurrency stuff. So there's going to be 3 major parts to this. I want us to implement our own locks. I want us to build locks up from scratch. So we're not going to use pthread mutex here. We're going to be building our own locks, implementing an API to build our own locks. We're going to be implementing our own thread API, but the issue that we're going to run into immediately with building our own thread API is that we're not going to actually have true multi-threading. Everything that we do in this assignment is going to be limited to exactly one thread in terms of what actually gets run on the processor, in terms of actually what gets run on the system. As far as our system is concerned, everything will be contained within a single thread. But we're going to have many threads of execution within that one thread. And we're going to be able to do rapid switching between these tasks to basically make it seem like we have multi-threading within this single thing. Once we've got some basic threading mechanisms, then we're going to start thinking about how to schedule those threads. So this is where we then get to implementing scheduling policies given the threads that we've got. So the main things that I'm looking for us to be able to do for this assignment or to assess you on is I want you to be able to write code that uses some library calls to create and manage threads. We're not going to be using pthreads for this, but you will be using pthreads to evaluate some parts of what you're doing. I want you to write code that uses something like pthread mutex lock to protect a critical section. So I want you to be able to use an interface that looks a lot like pthread mutex lock to be able to do this. I want you to be able to use atomic hardware instructions to implement a lock, and I want you to be able to write some code that will implement some scheduling policies for the threads that you're working with. So let's take a look at what this looks like. There are 3 interfaces that I'm looking for you to implement here. The first one is nqpthreadlocks.h, then nqpthread.h, and then nqpthreadschedule.h. I'm going to take a look at each of these in a moment, but I do want to spend some time dwelling on what I'm asking you to do for each of these things. The first part is I want you to implement locks. I want you to build your own locks from scratch, where from scratch here is in kind of a little bit of air quotes, in that we're going to have access to some hardware instructions that give us atomic operations like compare and swap and test and set. There's a header that has been added to C recently that is called stdatomic.h. Recently here this is a C11 thing, so it's been around for about 13 or 14 years, I guess, but it's recent in terms of C, the language. stdatomic gives us some important things. It gives us an atomic flag. This is something that we can use when we're doing testing and setting. And it gives us access to functions like atomic flag test and set. When we're looking at lock implementations in our textbook, we're describing this idea of spin locks using test and set, atomic test and set. And this is effectively what I'm looking for you to do with this assignment, is to implement atomic test and set as a locking mechanism, as a spin lock, where we're implementing the interface that's defined in this nqpthreadlocks.h file. When you're initially doing this, I want you to implement these as pure spin locks. So like literally just the loop that's spinning while it cannot get access to the lock itself, to that atomic value. And for your initial implementation, I actually want you to write some code that uses the lock that you have implemented. So the code that you write that uses the lock that you've implemented, I'm giving you permission to copy some of the concurrent code samples that we did in class to test your implementation of locks. So this could be anything like the code where we've got 2 threads that are adding or counting numbers, but we have to put a lock around it to make sure that we get the correct value as output. It could be up to like the concurrent list insertion stuff if you want, but I'd say take it easy on yourself and just pick the easier one to work with, which is just the counting one. I'm looking for you to actually write some code to verify that your implementation of locks works correctly. But eventually, as you're building this up, your schedule implementation or your lock implementation should yield its access to the CPU as opposed to being just a pure spin lock. So your initial implementation should be a pure spin lock using these atomic things from STD Atomic, but then eventually what you should do is switch to make this yield the processor if you're not able to acquire the lock in the thread of execution that you're working with. I'm going to pop over here and I'm going to take a look first at NQP thread locks.h. So we're defining this type, an NQP mutex T. NQP mutex init is a constructor function, so you'll have to set up whatever you need to set up for using an atomic flag and an atomic instruction here. NQP mutex lock and NQP mutex unlock here, or destroy and destroy are kind of like the same things as you've seen with doing pthread locks. So acquire the lock with NQP thread mutex lock, and then unlock the lock or release the lock with unlock. The try-lock function here, the main difference between locking and try-locking, both with this and with pthreads, is that try-lock will always return immediately. Try-lock always returns immediately, and it says whether or not you were able to acquire the lock. If you're not able to acquire the lock, you do something else, but the difference between a spin lock implementation of the mutex lock here and try-lock is that this is basically a conditional statement. This is a loop structure where we're looping on the spinning operation that we're doing. The destroy function down here is going to be like a destructor for the mutexes that you have initialized with the constructor function. So this is the first part of the assignment, to implement some lock structures and then write a little bit of code to evaluate whether or not your lock structures work correctly. This is not a ton of code. This is not a ton of code to implement it. It sounds like it's a lot, but it's not a ton of code. In terms of implementing pthread mutex, or the NQP thread mutex lock, it's about 3 lines of code, because it's just a spin loop. It's just a test and set with a while. I'm telling you how to do it right now. It's just a test and set with a while, and then just do nothing on the inside until you can get it. I'm going to go down to the bottom, and then I'm going to come back up here again to talk about more of the stuff. So for assessing the implementation of locks, I am initially starting with the graders are just going to look at your code and see if you've used the atomic instructions approximately appropriately to give you some minimal credit for this. But to get the top level, what I'm looking for is that you are you're writing some code to actually assess the correctness of your locks, to make sure that they actually enforce mutual exclusion to get to that point. So that's it for locks. Again, this is not a lot. It seems like it's a lot because there's a lot of me shouting here at the front of the room, but in terms of the implementation of these locking structures, it's quite small. There's not much to the spin locks that you've got, and I'd recommend that you look closely at the textbook chapter on lock implementations to see what that looks like. Once you've got locks, then we can start to do threads and scheduling. Then we'll start to build up our own threads and scheduling stuff. This is going to be a Linux-specific thing. The functions that I want you to use for this, they are available on Mac OS, but they have been marked as deprecated quite a long time ago, and I don't think that modern Mac OS will even let you compile code that uses these functions, but Linux will still support it. Have you tried already? Okay. So modern Mac OS won't even let you compile the code that uses these functions. But Lima should, because Lima is going to be a Linux implementation under the hood. If you haven't set up Lima on your Mac, I would strongly recommend that you do that. Otherwise, you're stuck working with Aviary for everything here. As I said, with this implementation of threads, it's not true multi-threading in the sense that we're going to have multiple threads running on multiple cores at the same time without air quotes. This is very much the contrived situation that we have in our textbook, where things are running giant air quotes at the same time. We're just switching around between them very rapidly to be able to make it look like things are running at the same time. The implementation that we're building here is not preemptive. It's a cooperative multi-threading implementation. I tried very hard to do preemption, but it would just lead me to getting seg faults constantly. And I don't want you to have seg faults constantly and to have to deal with that pain. I believe it's possible, but I didn't want to spend any more time trying to make it work. I'd rather just do preemptive, cooperative multitasking as opposed to trying to force preemptive multitasking to work. So the way that all this is going to work is that you're going to start by building up threads. To build up a thread, you're going to want to have a thread control block. You're going to want to build your own thread control block structure to make sure that you have access to important properties about the threads that are running in your system. The two main things that you need initially when you're working with threads and building up your thread control block are a context. This is the state of the registers of the machine as the thread is starting. And then you also need to have a stack for each of the threads that get run in your system. There's a couple of functions that you're going to be using to accomplish this stuff. The first one is this function that's called getContext. GetContext is a function that's provided by our standard C library that gives us an instance of a uContextT. uContextT is the machine context. This data structure contains all of the registers that are on the CPU so that you don't have to know or care about writing assembly language to get the registers off the CPU. You can just call this function and it will populate a data structure for you to use. It gives you access to ultimately this mContext structure. You don't actually even need to know what that structure is internally in terms of what we're doing. We get to just call this function and get this machine context and not have to worry too much about it. We can get access to this machine context, but the context that we get when we call getContext is literally the state of the machine when we called getContext. And that's not a useful threading thing because that's just going to give us the context of 3 lines ago as opposed to something that we want to do. And so the thing that we're going to have to call next is this function called makeContext. MakeContext takes an instance of this uContextT, and then it takes a function pointer. And the function pointer that it's taking is where it should put the stack appearing to start. So after we call getContext, we can add a stack to the context that we've got. We'll initialize and populate. We'll initialize a stack. We will declare some amount of space for the stack to be used. We do not have to build a stack ourselves. We just have to allocate memory for the stack to be placed into. MakeContext, once you've filled in that stack with an initialized area of space to use, MakeContext will manipulate the stack and the state of the machine in this uContextT to begin executing in this function pointer that you have. This looks a lot like pthread create. It looks a lot like pthread create because it's approximately what pthread create is doing underneath the hood. It's taking the context of your machine with clone and it's changing the stack and the current program counter so that you start executing inside that function instead of continuing where you were before. So you'll get a context with getContext. You'll allocate a stack probably as a file scope array of bytes. You'll put the stack into the context that you get back from getContext, and then you'll call makeContext to say you should start executing code here instead of what we're doing right now. Once you have that, then you can start calling this other function that's called swapContext. SwapContext will take 2 contexts. It takes an instance of the context that we're in right now and the thing that we want to swap to. And then it never returns. It never returns in the same way that the whole exec family of functions don't return. When we call exec, we're saying replace our address space with this other code. When we call swapContext, we're saying start executing in this other context, but stay in the same address space. Once you've got some threads of execution, then you can call this swap context to be able to go back and forth between different contexts and do this switching very rapidly. This is all something that I would strongly recommend that you take a look at the manual page for make context and swap context, because if I scroll down to the bottom here, it will give us some minimal structure and an example of how to do things like allocate space for the stack and put the stack inside the context structure that we've got. This also gives us some minimal example of how to do some kind of basic context switching with multiple context structures that we've got here. For this, what I'm looking for you to implement is this nqpthread.h interface. nqpthread has a type that I want you to work with and define internally as your thread control block. And then there's two functions here. There's thread create and there's thread join. So the same kinds of things that we were doing with pthread stuff. I've got some code in this sample repository here that uses this interface. So this is called nqpprinter.c. And this is something that will create two threads of execution with the code that you're implementing, and then ask it to start and then wait for those threads to finish. In terms of the assessment of this, as you're going through it, when you're building threads and then starting to do a little bit of the scheduling stuff, they start to get a little bit tied together in terms of how things are working. What I'm looking for you to start by doing here is to initially just have the grader take a look at your code and see if you've done something with get context and make context and swap context to see if you started working on this. But then eventually what I'm looking for is for you to be able to have two threads of execution. Two threads of execution that maybe start and then just swap back and forth between each other, but the only way to terminate your program is to hit Control-C on the keyboard. So we never get back control into the main thread of execution that we've got. We just keep switching back and forth between these two threads of execution because they keep yielding for each other. Once that starts to be implemented, then what I'm starting to look for is that you've got this structure where the threads that are switching back and forth between each other are maintaining state upon each call. So initially, when you're building this up, it's going to look like you've got two threads that are just switching back and forth between each other, and then they don't have any state. So the counter is going to keep starting at 0 instead of starting at some number that you got to before you yielded and swapped off. The next point is going to be to have that be, make it look like it's continuous. So they're going to stop running something and then they're going to start running something again from the last number that they had. And then eventually what we're going to have is many threads of execution that are starting to run in the system. And then eventually our main thread of execution will regain control. And then things will kind of politely and cleanly exit after that. I'm going to go back up one last time to the scheduling policy part. The scheduling policy part is that I'm looking for you to, once you have these thread concurrency primitives, is to start implementing some basic scheduling policies for them. I'm looking for you to implement 3 scheduling policies here: first in, first out, round robin, and then the multi-level feedback queue. The first in, first out, round robin, and MLFQ are kind of slightly different in that FIFO, as we've seen before, is not a preemptive scheduling policy. And so with this one, what I'm really looking for is that you just keep scheduling the same task until it actually finishes. So the task is going to try to give up control, but you just give it back control and keep going until that task has called an exit function. And then round robin and multi-level feedback queue, these are both preemptive. And so as the process is yielding, or as that task is yielding, I want you to pick a different task to go on the processor. One of the things that we're going to have to keep an eye out for when we're starting to build this up is that because we're doing this swap context, we're making this context, we're populating it with a function pointer and its own stack, and then we are switching to that context. The only way for our main thread of execution to get control again is for us to have the main thread of execution be something that can be scheduled in the system. And this is kind of implied in the structure that we've got here. So you're going to have code that will call this NQP thread create function a bunch of times. But the main thread of execution itself is kind of just sitting around in the background. And we do want eventually to be able to get back to the main function so that we can exit and wait for threads to finish. You're going to have to initialize a thread control block for the main thread of execution using the same kind of approach as what you're doing with the thread create function. So using that get context function. But the main thread of execution doesn't have to have things like a stack allocated for it because it already has a stack allocated for it when you start the program up. There's a couple of special cases here. So with FIFO specifically, the main thread of execution has to be last always. It always has to be last because we want it to block when it's waiting for its children or the threads that it's launched to finish. And if we get into a state of scheduling our main thread of execution to block before it has its children finishing, it's just going to get stuck. It'll just get stuck. It'll be waiting forever for them to finish, but they'll never get control of the processor again. So as you're implementing this, you'll have to have some special case for your main thread to be either the last thread of execution or just something that doesn't get scheduled until there's nothing left in the queue to be scheduled. The round robin and MLFQ policies, these are going to be sort of what's described in our textbook. And the idea is that our threads of execution are going to call a yield function to give up control as opposed to having preemptive multitasking. And when they call the yield function, you'll have to select which task gets to go next based on the policies that we've got here. I've got some settings that you can use for your initial implementation of MLFQ. And when you're doing things like trying to measure how much time a task has spent running in the current queue, you can use some real-time functions in the system. So there's this function called clock get time that gives you high precision time from a Linux system. It measures things in nanoseconds, and we're thinking about microseconds, so keep in mind the differences between microseconds and nanoseconds. The interface that I'm looking for this one is in NQP thread schedge.h. So we've got the different scheduling policies listed here in this enumeration. And the overall structure of this is that we're going to call this NQP schedge init function to start. Maybe. We don't have to call this. The default setting is going to be the one that we have for kind of like starting the system up, which is that we're just swapping between two threads. We're just constantly swapping between two threads and never returning to our main thread of execution. The other policies may have settings that are passed to them. The only one that has settings in our case is MLFQ. The other policies don't have any settings for us to pass. So this second argument that you pass to this could be null. But if it is something that is the MLFQ policy, then it must not be null. This function is going to be our explicit statement of, I've created these threads. Now you should start scheduling these threads. So you will switch to one of these threads of execution that are in the queue that I have. The threads themselves are going to call NQP yield and NQP exit. NQP yield says, I'm going to give up control. Somebody else is allowed to take over and start running. And NQP exit says, I'm all done. You should remove my thread control block from the list of possible jobs to be scheduled on the processor. The assessment for this looks a little bit like what we had for the other things. So each of the policies that I've got is, whoops, I'm going to have to come back and fix this. My table got messed up here. Each of the policies themselves are going to be assessed independently. So I'm not like looking for scheduling as this one big blob of something. I'm more looking for each of the policies that you've got here to be assessed.
Because we don't press enter.
It's actually, I mean, maybe, but it's more like the plugin that I use in Vim for doing table modes constantly messes with my buffer. And if I do things like accidentally put a space in front of one of the pipes in my table, it shifts everything over and it messes everything up. I'll come back and fix this.
Next bit between queue, there's two straight lines.
Here?
Yes.
Oh, yeah, maybe
Yeah,
I've got,
that's probably what it
well, no, this is the next line. Now we're getting in the weeds of Markdown here as opposed to anything else. I will come back and fix this, but,
Markdown.
yeah. Take comp 1002, and then yes, that is the Markdown class.
I think we're allowed to take that.
You are very much allowed to take that class.
It doesn't count.
It's a science elective. It's a 1000 level science elective.
I think it doesn't count towards our credit hours because like we are in the declare order to declare the major, so like
I know about this course intimately. It's a 1000 level science elective. Comp 1500, that's different. Comp 1002 is the lab course, and it should not affect anything to do with your graduation. It's a weird number of credit hours because it's only 1.5 credit hours, but it should count as a science elective. I will be teaching it in the fall, yes. Yeah, yeah. 1006 I'll be doing in the winter, yes. Okay, we're digressing. The assessment of the first in, first out policy is you can kind of get most of the way there without actually really implementing too much. So like basically taking a look at what you have implemented is going to be level 1. And then level 2 is going to be that we want to see that you've got some minimal implementation of the policy, but not all tasks may complete, and then eventually all tasks complete. The round robin assessment is the same sort of idea, but what we want to see here is that the tasks do get swapped out. So some little amount of work will be done, and then the next one will start taking over, and then the other one will take over, and then the other one will take over. So we want to clearly see in the output of something like this adding or letter program that there is context switching taking place while the threads of execution are running. And then the multi-level feedback queue, there's a little bit more detail here in terms of we want to be able to see that the tasks are actually moving around in the queues that are in the multi-level feedback queue. So I want to see that a task that is in the high priority queue will eventually get moved down to the lower priority queue. And then I also want to see that they will all eventually get boosted back to the top. They're all going to get put back into the highest priority queue. One of the things that you might notice when you are implementing the multi-level feedback queue, specifically with your main thread of execution, is that the main thread of execution will always be stuck in the highest priority queue because it appears to be an interactive task, depending on how you've implemented things. It appears to be an interactive task because it's constantly yielding. It's trying to wait for the threads to finish, so it just gives up the time that it has on the processor. So when you're implementing MLFQ, you might want to think about things like adding special cases for the main thread of execution. Either spend some time doing nothing, or just don't count the time and force it to be in the lowest priority queue all the time. Yeah.
Would you prefer to use a priority queue for MLFQ, or is there a specific data structure you use?
It's up to you. So I don't really have a strong preference for priority queue. I don't have a strong preference for a list of queues where each of the entries in that list have a different priority. It's kind of up to you to decide what you want to implement for this.
What would you do?
I would just use a single priority queue to implement this as opposed to having 5 different queues, just because there are fewer moving parts.
So basically a heap.
I mean, I implement it as a linked list because I love linked lists. It's linked lists everywhere. But if you want to implement it as a heap with an array, you're welcome to.
Yeah, that probably would be one.
Okay. I don't like doing that because I don't like running out of space. Yeah, yeah. Okay, so this is a lot. This is a lot. One of the things that I am going to try to do is, like I did last time, try to save a little bit of time each week for having questions about the assignment in class. There's a lot going on here. Like I said, the locks part looks like it's more than it actually is. The locks part is quite small. The threading implementation part is a little bit mind-breaking in terms of like switching back and forth between contexts that you created, but once you take a look at the manual pages for the swap and make context functions, and I'd recommend you try just entering their examples to get an idea of what's happening between those things. Once you have that basic idea going, it becomes a little bit easier to get to the point of doing the thread control block and then beginning to implement the different scheduling policies. Yeah.
So with the way you explained, the way I understood it is that the main thread will be creating all the threads and then afterwards calling the scheduler so that they're then being scheduled.
Yeah. So when I was looking at this, and I also need to come back and fix this. When I was looking at this, there should be a line right here that says start sketch. There should be a line on line 39 here that says to start the scheduler. So there's two things I have to do when I get back to my office, fix a table and then put that line in there. But we're explicitly saying you should start scheduling tasks. So I'm finished making threads, now you should start scheduling tasks. We don't want to do it any other way because if we started scheduling tasks here, the task might start. We don't want it to start yet. We want to have some control over when the tasks are going to be scheduled. Yeah. Are there any other questions before I move on to anything else? It's an assignment. It's an assignment, yeah. Yeah. I think this is super cool. Just to be clear, I don't want to mince words. I think that this is going to be a challenging assignment, but I think it's cool. I think it's cool. I think it's really, really cool to be able to take a lot of the stuff that we've been talking about and using and actually build that stuff up.
It'd be cool to make the shell do stuff.
I thought about it. I really thought about it. And I also really thought about stuff like making our file system support writing with multi-threaded code.
Oh, yeah.
Yeah, and so I pulled back pretty hard here in terms of what I was doing. But I think this is awesome. Like, when I wrote this code and I saw the letters A and B switching back and forth as it's printing out was just like, that is awesome. And it's literally just the letters A and B being printed out over and over and over again. And like actually seeing this happening and like knowing that this code that I wrote made that happen is just very satisfying. And so I hope that when you get to this point, you are feeling that same level of satisfaction in terms of getting this stuff working. Like I said, I will have some more time for questions about this in other classes. What I would like to do right now is to switch gears back to taking a look at our scheduling policies. Whoa, okay, all right. Last week, we took a look at these two non-preemptive or cooperative scheduling policies. The context of what we were looking at with first in, first out and shortest job first as non-preemptive isn't really so much that they were cooperative tasks. These tasks weren't voluntarily giving up control of the processor at some point. They just ran through to completion and then eventually finished, and then we were able to get control back and switch to another task. What we found out about these two policies was that first in, first out was a fair policy, assuming that all tasks are fair. If we remove the assumption that all tasks are fair, then it's not a fair policy because we could have this implementation of an infinite loop, either intentionally or unintentionally, blocking everybody else from ever getting access to the CPU. Shortest job first, assuming that our tasks were fair, we couldn't say that this policy was fair. With this degenerate situation of I've got a task that has a lot of time left and an infinite number of jobs that have much less or any number less time than it, even 1 unit of time less. It will just always be less than that task. And so we have this unfair situation where that one task that has the most amount of time never gets scheduled because we have all of these tasks coming into the system before it. I'd like to take a look at shortest time to completion first today. And what I want to do with this is kind of asking the same sort of questions about it. So I want to be able to measure this idea of turnaround time and response time. Again, I'm not going to do this in class, but this is something that I would expect you to be able to measure about a task that's been run through a system, doing the differences between the time that the task completed and the time that the task arrived in the system, and then also for response time, the time that it was first run and the time that arrived in the system. The more important thing that I really want to think about here is fairness. So does every task eventually get some time on the CPU, given these two constraints of all tasks are fair in the system, and then given the constraint that we cannot make that assumption that all tasks are fair? I'm going to do the same thing as what we were doing last time. So I've got our incoming workload here, and I've got more printouts here. I've got more sticky notes if you want to follow along, but I've also put this document up on the course webpage so you can click and drag stuff around if you want to. The shortest time to completion first is a lot like the shortest job first policy. In our shortest job first policy, we have a priority queue in this system, and the priority here is going to be measured on the task in the system that currently has the least amount of time left. And this is one of those unrealistic assumptions that we have, is that we can measure how long these tasks take. As jobs are added to the system in shortest job first, we were finding ourselves rearranging this task queue to move tasks that have more time to be closer to the back and tasks that have less time to be pushed up to the front. And the issue with this ultimately was that when a task gets control of the processor, it will run to completion before the next task is able to be scheduled. The shortest time to completion first policy changes this slightly. It is still basically the same as the shortest job first policy. It's still basically the same as the shortest job first policy, except we add preemption. Once a task gets some time on the CPU, we might actually remove it, even if it doesn't want to get removed or it's not ready to get removed. Tasks will be given a certain amount of time, and then they will be removed from the CPU and then put back into the scheduling queue itself. In terms of where they get put in the queue, it's still shortest job first ordering. We're still going to put the job that has the least amount of time remaining into the queue at the front. But we could potentially be taking jobs off of the processor with our time slice or with our quantum. And so I'm going to prime this. I'm going to start with time is 0 here, and I'm going to start getting us set up, and then we'll do the same sort of mechanical exercise, but I think I'll probably speed it up just a little bit this time, just to keep things moving along. So with shortest time to completion first, and at current time is 0, our first task is going to arrive in the system. So task A has an arrival time of 0. It's showing up at time 0, and because there are no other tasks in this system, it's also just going to get control of the processor immediately. So its first runtime is going to be at time 0. Remember that last time we described this idea of this unrealistic situation where we have like free context switching and stuff. It doesn't take time to do anything with terms of switching tasks around. It just happens instantaneously. We're operating under that same assumption today. So task A arrives in the system, it gets put into our current task queue, and then it immediately gets to take control of the processor. I'm not going to step ahead by units of 1 here. I'm going to step ahead by units of 5. So at time 5, several things are going to happen all at the same time. The first thing that's going to happen is task A is done. It finishes at time 5, and it gets put into our completed tasks area. That means, conveniently for job A, that it never really got preempted. It just gave up control of the processor because it was finished. Task B and task C arrive, but this is shortest job first with preemption. And so task C, because it has less time allocated to it gets to go in front of task B. There's nothing currently on our processor, so task C gets to go right to the processor, and its first runtime is going to be at time 5. I'm going to skip ahead now to time 10. 5 units of time have elapsed, so there's 5 units of time remaining for task C. But at this point, we preempt task C. We take it off of the processor. Our quantum, or time slice here, is 5 units of time. And so every 5 units of time, we're going to take a task off of the processor. We will take the task off of the processor, and we're going to put it back into our current task queue. The other thing that happens at time 10 is that task D shows up. But this is still shortest job first. And the shortest job in this system right now is task C. And so task C just gets to go right back on the processor. We took it off, but it just gets it again because it has the least amount of time remaining. It's the least amount of time to completion remaining in this system. Task D gets to go before task B because it has less time than task B has. And now we're all done in terms of the change of state that we have at time 10. I'm going to set our time now to 15, and I'm going to say that at some point in this period, task E has arrived, and it's going to get to go to the front of the queue here. Task C will finish. There will be no time left, and so it's going to finish at time 15. And it also isn't really being preempted here because it's just done. There's nothing left for it to do, so it's going to be taken off of our processor. In this instance, we have these 3 tasks. Task E is the thing that has the smallest amount of time left. And at this point, I'm actually just going to stop with doing shortest time to completion first, because it's going to look exactly the same as shortest job first. When we put task D on the processor, it's going to lose 5 units of time, and then it will go back to the queue and have the least amount of time, and then get put back on the processor again. Here's my question for you. Given what we know about shortest job first, if we make the assumption that all tasks in this system are fair, so that means, again, to me, that all tasks will eventually complete. There's no unintentional or intentional infinite loops. It will finish eventually. Well, we have an infinite number of tasks, and you're already putting your thumb down. Yeah, is this fair or not? Is this a fair policy or not? So yeah, no, this is still not a fair policy for exactly the same reason that shortest job first was not a fair policy. What was happening to task B with shortest job first is still happening in shortest time to completion first. We just get into the state where we have tasks that might show up before it that themselves are going in round robin because they're going to have a little bit of time less than the other ones that are currently in the system. So we're going to end up in this state where task B, even though we're able to take stuff off of the processor, will never get to run because there's an infinite number of tasks that keep showing up before it, and it's stuck holding the door to McDonald's and starving to death and not being able to place its order for its McNuggets. Yeah, I like the idea of anthropomorphizing these tasks so that they want to eat chicken nuggets. The last policy, I guess, that I want to think about, and I'm not going to step through this because we've got 1 minute left, but I will describe it to you, is round robin. With round robin, what we're doing is a little bit more like what FIFO was. Tasks get added to the end of the queue in the system, but we preempt them. And when a task gets preempted, it gets put at the end of the queue. Given just that information, I want you to to try and make a decision right now about whether or not you think that this policy is going to be fair, assuming that all tasks are fair. Yep. So this is a fair policy, assuming that all tasks are fair. What about if all tasks are not assumed to be fair? There might be something that has an infinite loop in it. This is still a fair policy. This is still a fair policy because even if something has an infinite loop in it, it's going to get preempted and put at the end of the queue. So something that gets added will eventually get access to the CPU because it's doing this whole round robin thing where we're allowing other tasks to be able to take over. All right, so at this point, you should know more about assignment 3. You should be able to evaluate the performance of scheduling policies, and you should be able to compare and contrast different scheduling policies on different workloads. That's it for today. I hope that you all have a great rest of your day, and I will see you all on Wednesday. Bye, everyone.